Welcome, I'm Bill Wake. This is my weekly summary of what we've been doing on Twitch lately. So what is this project? Well, we wanted to invent a fourth-like language I'm calling 10th. That's mostly done. We wanted to create structures for primary and secondary or compound words. That's done. We wanted to develop an inner interpreter that interprets those structures. That's what we finished this week. So that's done. Done may be a relative term for some of these, but we'll address whatever's remaining when we get there. Now, this week, we're focused on building a dictionary for primaries and secondaries, including search, and that's in progress. Upcoming, we'll need to build a compiler from 10th, the language, to the structures. It's not a very tricky compiler because the language is mostly just tokens and then look up in the dictionary. There's a few twists for control structures, but I don't think it'll be too hard. Once we have a compiler, we're going to develop an outer interpreter, a redeval, print loop, REPL that we can use to run programs. And then we'll create a 10th unit test framework and test drive a small to medium-sized example in our language. Now, why am I doing this? Well, a few reasons. One is there's this threaded code approach that I've wanted to do for a long time, and this is my chance. I wanted to learn a little ARM64 assembly language. And then I wanted to try TDD in a couple unusual places. One assembly language, the second in this sort of stack-based language. So this past week, one thing is I realized we'd been storing a pointer to the address of start2d rather than the address of start2d. So our depth of pointers was off a little bit. Once we realized that and fixed that, everything started working again. So we updated all tests to use this new arrangement. And then we moved on to the primitives, just a handful of them, but dupe is duplicate, subtract, multiply, and test for not equal. And we chose those particular ones because they're the ones you need to write a recursive program. We wrote a factorial program, and it worked the first time. It was almost disconcerting how easily it worked. So with that, we have our primaries and secondaries. We have the ability for secondaries to call secondaries and primaries. And the secondaries they call can include themselves, so it's recursive. We don't handle doubly recursive where you're forward referencing something. I don't know if we're going to worry about that. It's something we could address, but it's not a key thing for my language, so I'm not gonna worry about it. And finally, we started building the new dictionary. So the one we've been using so far has been restricted to just the key pointers. It didn't have anything to let us search a dictionary of words or names. So we've started in on that. First for the system terms, we got that basically together, but we haven't put them all in a list yet. And we started working on dictionary search, so you can look up a system primitive, and that'll be a core piece of the compiler. We haven't done the one for users, but I don't think it introduces a lot of new issues. So what was that problem with the addresses? Well, our secondary structure is basically a list of calls to or a list of the addresses of other functions to call. And the first cell is part of the header, and we had a pointer to the address of start2d. Start2d is the assembly language routine that knows how to walk through that list and call the other methods or functions more accurately, I guess. And then each of those cells, the rest of that secondary contains the pointers to the functions. So pointer to the address of some secondary, or a pointer to the address of a primary or another secondary. And then at the end, there's a call to N2D, which is the sort of return statement that corresponds to start2D. In assembly language, it's a little tricky to keep track of pointers to pointers to pointers or any of that stuff. And that's what got me burned. I had it in my head that everything was going to be pointers to the addresses of these things. And you don't really want that. What you want is that first cell, the header, is an actual pointer to the function you're going to call, not to an address containing that function. The others, however, are pointers to addresses still. So I missed that distinction mentally somewhere along the way. And once we fixed that, then it was clear how to call the right thing, and everything fell together correctly. All right, then we did these primitives, and they're pretty simple. So first, subtract. We have a data stack, and there's a macro that says how do you pop the first two elements off the stack. So we'll pop x1, x0. We'll subtract x0 equals x0 minus x1. We'll push the result, and you're done. And then multiply is basically the same except multiply. And yeah, I'm ignoring overflow. Again, I feel like I know how to solve it. There's a comparison test you can do that checks for overflow, and we could, throw an exception or blow up or however we want to handle it. But I'm not too worried about that. It's not. I'm using this as a vehicle for other things. I'm not trying to be a complete full programming language, I guess you'd say, or a complete safe one. I suppose C ignored overflow for a long time too, and they went far. All right, and then the next couple were duplicate. So duplicate, you just look at the top element, and we put in x0 is the register, and then you push that x0, and now you've got two x0, whatever's in there on the top. And then finally, NEQ is a little trickier. This one is basically we want to put 1 or 0 on the top, 1 meaning it's not equal, 0 meaning they were equal. So again, we pop the top two elements, then we do a compare instruction, and then we have this conditional set that's built into assembly, to ARM64 assembly. C set x0 NE says set x0 to either 0 or 1, depending on the condition NE. And once we have that result, 0 or 1, we push that back on the stack. And then an if statement or something else can consume that logical value. The first implementation of this didn't use CSET. It did a bunch of testing and then branching around and so on. But CSET makes it work out very easily. So it turned into a nice small routine with no jumps. Now, recursion was definitely the fun part of the week, I guess you'd say. So on the left, I have a definition for factorial and written in this fourth-like language, just reading down. So you'll duplicate the top of the stack, then push a 1, and then test for NEQ not equal, and so on. So behind the comments, though, I tell what's on the stack, so to keep track of it. So we go in with the argument on the stack. We duplicate it so we can manipulate it. We push a 1, and then we test not equal. So the first not equal is, does A equal 1? Okay, if it's not equal, if A is not 1, it's going to go through dupe and 1 sub and all that. If A is equal to 1, we go to the end. Well, 1 factorial is 1, so in that case, we're returning a 1 on the stack and everything's good. If we have not 1, then we duplicate what's on the stack, so we can subtract 1 from it. So dupe 1 sub puts A minus 1 on the stack. And then we call factorial, that's the recursive call, and that turns the top argument, A minus 1, into A minus 1 factorial. And once we have A minus 1 factorial, we multiply the top two things on the stack, A times A minus 1. And by definition of factorial, that's also A factorial. So you get to the end, and either path took us to A factorial on top of the stack. The implementation, so remember I said we haven't done the compiler yet. So basically I have to kind of hand compile this into our primaries and secondaries. And the two components of that, the first is a dictionary. And we're going to list each system routine we use as a new entry in the dictionary. So N2D, dupe, push, and so on. And then the secondary definition, it's going to define L factorial using the dictionary and using the start2D routine. Each one of those lines, like the first one, secondary add 1, well, we have to go up to the dictionary to see what 1 is. Oh, it's dupe. Okay, so we've got the dupe statement in our secondary. The second one is 2, is push. Well, we can't just put a number. A number isn't an executable thing. So we do a push followed by the next word containing the literal 1, and that's what gets pushed. And then 3 is NEQ, and so on down the way. The two that stick out, secondary target 13, that's the address to jump to. And if you counted this out, the 13th one is the call to N2D. And then the other one that's funny is secondary address L factorial. Well, that's our factorial function. So that basically adds the secondary, which is factorial, to the list. The rest of it matches up, pretty close. I mean, the comments are basically the code on the left. But as we finish the actual dictionary, we probably could make the standard dictionary and then make our calls just reference those by label or something. That would be a little easier to tolerate. But this is good for now. And like I said, we typed it in and it worked. It was nice. Unusual maybe, but it was a good day that day. The day before we were debugging those pointers, that was not such a good day. We've had various dictionary structures I've described a couple times, but now I'm settling into what I really concretely want. Each entry is going to have a header, and the header has three cells: a link to the previous dictionary entry, a pointer to the name of the routine, and then the address of the code that we're going to run. Those three together form one header. Now, in the version I've shown before and some other implementations use, the code actually follows directly in the dictionary, but we pull it off to the side because our linker is kind of not up to the task. That's fine. All right, and then the links to previous, that gives us a singly linked list that we can walk through and look for a name. All right, now secondaries actually have the same header. First one's a link to previous, a pointer to the name of the routine, the address of code, which happens to be start 2D or our start secondary routine. And the entries for it will be just following the header. So it'll be more of a, a header being at the head of things, as it were. All right. And that's really just that a list of addresses. And the addresses are the third cell of some header. So if, say, the first one is N2D, we're linking to there that gives us a pointer to the N2D function. And the reason we're using the pointers is this way primaries and secondaries both call the pointed to address. They both can find them the same way, both use them the same way. That keeps everything a little simpler. All right, well, let's look at the code we have so far. It's not much. The system dictionary, we have a sentinel that's 3 zeros in a row, so that's sort of an empty header, and then fill 300 reserves enough space for another 100 entries. I don't think we'll have 100 primitives, but I don't want to worry about it right now. And then initializing the dictionary is very simple. X21 is sort of a global pointer to the system dictionary. Global because we need it to do our compiling and stuff like that. It's not super specific to any local bit of code. The way you build a dictionary header, you're given the name, which is a string, and you're given a code address. So we have to fill in those three blocks. There's a little bouncing around to do it the right way, but the first step we do is we push that link pointer. So the current value of X21 is a pointer to a cell, and we're ready to go to the next cell. Well, we write that in at the pointer plus 24, which is 3 8-byte words, 24 bytes. So that's the pointer for the next header coming in. All right, and then we adjust our X21 so that we do move down to that pointer. And from there, we're going to put in the name, pointer to the name. Well, I've got ldict header underscore \at. Well, @@ is part of the macro facility. It says generate a new number for every time you call this macro and use that same number throughout. So ldict header @ goes down to the bottom there. Ldict header @ is going to be defined as an ASCII Z name for the name we passed in. And that's stored at the second byte, 8 off of X21. And then the third byte is the code address of the routine we're going to call. Well, we got past that in, so we load that in and store it in the third byte of the header. So this creates one new header and leaves X21, the dictionary pointer, pointing at the last, the most recently created header. So in our next sessions, first priority is to get dictionary search working. It shouldn't be too bad. I think I know why it wasn't. I always think that. Then we're going to build a dictionary with all the existing primitives. Once we had that, we probably could put those in the tests. I don't know if we will or not at this point. And then we need to make the dictionary work for secondaries. The header part's the same, but putting in those lists of routines, we don't have a facility for that yet. And once we have that, I think we can work on the compiler and get at least 75% done. I'm not sure we have the facilities for everything, but the core bit of an input stream, breaking apart the tokens, looking them up in the dictionary and creating new secondaries, I think that should be pretty straightforward. Again, I'm always an optimist, but you kind of have to be. Thanks for joining me in this review. If you want to join us live, that's Monday to Thursday, 2 to 4:30 p.m. EST. I don't know when daylight savings time starts, but I'll switch to daylight savings time when it does, or 7 to 9:30 p.m. UTC. xp123.com/Twitch will get you to the live sessions, or you can go to xp123.com/YouTube and get the old sessions, I think a few weeks behind, time delayed, and lightly edited. All right, thanks for listening. Bye-bye.